wait till he's back. Oh, okay. All right. So let's start with part two. I don't know. While you guys were having coffee, were there any like, whoa, I didn't understand anything of the last talk. What was this? Any questions that come up new? Yeah. 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 Usually you can only couple to optical phonons unless you do something sort of to sort of make an artificial optical phonon by some kind of nanostructuring. But the problem is essentially shown here that you have to sort of match momentum conservation in a crystal momentum anyway. And the problem is that assuming that you're not too thrilled about just translating the sample across the room with zero frequency light, then you'd be more interested in the optical branch where it actually crosses here. So. Yeah, there are ways. So if you have you can have surface effects. Um, if you have some kind of like attenuation in any sense, also, then you can excite some acoustic phonons. It's a bit. I don't want to get too much into it, but it's possible under certain circumstances. But the sort of general idea is typically the most efficient coupling, anyways, to the optical branches. So yeah, I shouldn't say it's impossible to do acoustic because actually we at least tried to do an experiment where we drove an acoustic mode. It didn't really work that well, but it's at least possible to think about. All right. Any other questions? All right. All right. So let's. I'm going to shift gears to talk about sort of more technical aspects of terahertz, because I think this is the first talk about terahertz. Yes. Okay. I saw there's going to be one later. Um, Also, that maybe we'll talk about slightly different things and probably more about applications, I suppose. So I think this is a good opportunity to talk more generally about how this works. So I'm going to talk about generation and detection mechanisms. All right. So what I'm talking about is, yeah, this is sort of the generic what the hell is terahertz slide. So we're sitting, typically this conference is so far focused mostly in sort of the visible and near visible range. What we're talking about terahertz is frequencies. So these are cycle frequencies around 1 terahertz. That corresponds to about 1 picosecond period oscillations of the EM field. So these are a list of random things to do with 1 terahertz that's sometimes convenient to know. I think probably the most important to remember is the period, as I just said, is 1 picosecond. The wavelength is about 300 microns, which has a lot of sort of practical implications because this is actually a pretty big wavelength. And so focusing is kind of a challenge if you want very high fields. Wave number is 33 inverse centimeters in case you're a IR spectroscopist. The photon energy and the temperature are sort of in the range where we have sort of 50 Kelvin, corresponding to 50 Kelvin temperatures. So that's also somewhat relevant. All right, and then there are other names that it goes by depending on the community that you come from. Terahertz is a relatively new term over the last 20 years or so. Before it was mostly called far infrared radiation, at least by the optics community. All right, so there are a lot of different methods to generate terahertz radiation. I cannot go through them in 1 hour in any kind of detail. So you can, quantum cascade lasers is a very hot research topic that's very active. You can also just, you're a terahertz generator yourself because you are at a temperature. And so you emit actually quite a bit of terahertz radiation just by the blackbody radiation. These are not particularly, well, the blackbody radiation is particularly incoherent, of course. And so it's not really useful for what we're going to talk about is driving coherent phonons because we can't we can't use direct mechanism to imprint incoherent blackbody radiation onto a coherent phonon, at least not easily. So here I'm going to be focusing on lab-based, so not accelerator-based, high electric field coherent terahertz generation. Okay, so that's going to limit our options to a couple choices. And so what I mean by coherence, I had a long discussion in the coffee break about what coherent really means. It's not identical with coherent states. But here coherent means that what I mean by that is I can synchronize the phase of the electric field with the time zero in a pump probe experiment. Okay, so that's what I mean by coherent in this case. So it's coherent for the purposes of what we want to do. And so this is a necessary condition for generating a coherent phonon ensemble in order to do that, by a direct mechanism anyway. You can also have accelerator-based sources. It's worth noting because you can actually get really high fields compared to what you can get with lab-based sources in some accelerator-based sources. But of course, it's limited, more difficult to access, and it's more difficult to use in a pump probe measurement. But if people really want to know about that, I could say a little bit about that on the chalkboard maybe. All right, so one of the most sort of popular ways to generate sort of at least moderate field coherent terahertz pulses are called photoconductive switches. So this is a fairly simple kind of thing that you can easily sort of incorporate into an existing lab that already has an ultrafast laser. So what you do is you take a semiconductor substrate. So typically it's gallium arsenide with a particular kind of growth method to sort of control the carrier dynamics a little bit. And then you deposit some metal electrodes on the surface, and then you apply a bias field across that. And then you shine an ultra-short laser pulse somewhere in between the electrodes. This is sometimes it's combined. You see this with a silicon lens on top, but that's not really that important for the physics. The idea is sort of phenomenologically, you whack one side with terahertz, and then you whack one side with the laser, and then you couple out the terahertz from the other side. You can also couple out terahertz from the receiving side, just less convenient, because usually you have a problem with the optics. So the microscopic mechanism for this is fairly simple. So the idea is that you have a semiconductor, so you initially have, let's say, no electron hole pairs. It's, of course, you're going to have a few, but let's say you have negligible amount of electron hole pairs existing in thermal equilibrium. And we have this bias field, which generates an electric field that, in this case, we're going to say it's pointing from right to left, that exists near the surface. And then the idea is that you come in with your laser pulse, you excite some electron hole pairs, and then these electron hole pairs now see this electric field from the bias. And depending on whether they're electrons or holes, they're accelerated in different directions, so they're kind of torn apart by this electric field. And so you get an acceleration of charge that will result in the emission of electromagnetic radiation. All right, so that's the idea. So you bring it to drift velocity, that results in a current, and then you have a time-dependent current, and a time-dependent current acts essentially as an antenna that will emit radiation. And if you sort of make the time constant of the change in the current have a significant amount of frequency components in the terahertz range, that means you have to use a laser that's typically at least a couple hundred femtoseconds or shorter, and you have to pick a material where the acceleration to the drift velocity is reasonably fast. That's actually not a huge problem usually. You end up with this current density of states, this current density that, at least to some approximation, if you assume that the acceleration of the drift velocity is really fast, is essentially following the number of carriers generated. So this N of T is the number of electron hole pairs. And in this case, usually one of the mobilities is much smaller than the other. And so we only talk about the number density of electrons. And so the current is going to follow the time dependence of the current follows the time dependence of the electrons generated by the ultrafast laser pulse. And so if you have in principle, if you have a several hundred femtosecond laser pulse, you're generating carriers with a time on a time scale of that several hundred femtoseconds, which contains significant amount of frequency components in the terahertz range. So yeah, then you basically have a far field emission of radiation from that. So you get, this is in the far field. You have this electric field of the terahertz. That's the time derivative of the current density, and so that corresponds to a time derivative of this electron number density. And it would, in this case, in this particular case of this dipole antenna that I drew for sort of simplicity, you have a dependence on the angle of emission, where you have no emission, say straight up, and then you have a maximum at directions orthogonal. So that's the sine theta kind of behavior. This theta is just a geometric parameter. So you have, there's a lot of constants that I'm not so thrilled about getting into the details of, but one thing that it's the bias field and this time dependence of the number density of electrons is sort of important parameters. All right. So I'm not going to, I'm going to kind of going over this quickly because we don't really use photoconductor switches. I'm just sort of doing this for completeness. And because it's something that's sort of relatively easy to implement. And so if you really wanted to get into some kind of terahertz, this would be sort of the way to maybe jump in a cheap way. So at low repetition rates, you can get a microjoule or so of power out of the terahertz, which corresponds to about 10 kilovolts per centimeter peak field. You can do a bit better than this. I'm just sort of giving typical numbers for sort of basic designs. This is what the this is actually a current measurement of a detection mechanism that I'll talk about later, but you can essentially think of this as the electric field as a function of time. You get a broadband sort of quasi-single cycle response out of the system. And so you really get sort of essentially one oscillation of the electric field that's getting emitted. So it's a very broad, it contains a lot of different frequencies at the same time. Usually the frequency, the bandwidth is going to be limited by the phonons that exist in the substrate. There are some other factors that also limit it, but one of the major ones is the fact that your substrate, for example, gallium arsenide, sometimes has like an absorption in the terahertz range. In this case, gallium arsenide has an 8 terahertz TO phonon that is going to absorb a lot of stuff, and so that limits a little bit how far up in the frequency spectrum. So this is essentially a Fourier transform of this that shows the frequency content of this single cycle pulse. So you see a very broad frequency range that has some components up to maybe 3 terahertz, but then it really is very difficult at that point. All right, so that's photoconductive switches. Another method, so any questions about photoconductive switches? Maybe I should stop. Okay, it's all totally clear. Good. Okay, so the other method that I want to talk about, and I didn't make any really stupid mistakes for people who know more about this than I do, so that's also good. So optical rectification is another method that's used to generate similar kinds of terahertz pulses. Again, sort of single cycle pulses. And this slide is just giving sort of the rough outline of how that works, at least phenomenologically, right? So the idea is that you start with this is meant to be like an 800 nanometer Ti-sapphire femtosecond laser pulse. So that would be like the electric field as a function of time and sort of a scrunched up time scale. So you can't really see the individual oscillations. So this has a width, a certain width in time given by the envelope function on the order of say 100 femtoseconds or so, maybe shorter, maybe longer. And then you send it through a crystal. So in this case, this is one of the actual crystals that we've used before in our lab. And I'll explain a little bit more about what this crystal is. But let's just say, you send it through, and then the idea is that you get, in the end, a shape of electric field that has the frequency components of the envelope function. So the idea is the rectification, it's a little bit of a misnomer. I would say, rectification. I'll explain why in a minute. But the idea, at least the rough qualitative idea, is that you sort of rectify this electric field, and then you get the frequency components from that. And then there's some propagation effects that cause it not to match exactly that. What you're doing is you're taking the derivative and so forth. But that's the basic idea. All right, so how that works is you need to use a crystal that has a non-zero second order susceptibility tensor. So what you're doing is this is a second order nonlinear effect that takes place inside the crystal. So this is sort of linear physics. This is the second order physics and the expansion. And of course that means that you have to, for this mysterious green crystal, has to be has to not have inversion symmetry. So it's the same thing as for second harmonic generation. It's just sort of the opposite kind of thing. So that means you can't use things like things with like a diamond structure, for example, but you have to go to something. The simplest version of a non-inversion symmetric would be something like a zinc blende structure, I think. All right. So the idea, though, is if we just look at this contribution to the polarizability, if this is, so we're going to substitute in for our E of t, this is going to be our incident ultra-fast laser field that's oscillating around. So that's this thing. And then this is essentially the square of that. I mean, there's you can kind of, let's kind of ignore the tensor arithmetic. This is just the square. And so you get something like this, all right? And so it's not negative, obviously, because these are real valued electric fields, not complex ones, because we're doing nonlinear physics, and so we have to be very careful about that. So, and then the idea is if you take this second order response, that's essentially sort of what this is, sort of in a scheme, and you can kind of represent that as the sum of two different components. So you have the second harmonic component, which is what's maybe more familiar, which is what happens if you look at sort of if you look at sort of the local average frequency. This is going to oscillate at twice the frequency. But you also, if you sort of look at the sort of, if you average all those fast fluctuations out, you're left with this pulse here that will have frequency components characterized by the inverse of the width of the initial pulse. Okay, so that's going to be in the terahertz kind of frequency range. And so this is what we want to use. We want to throw away this and use this. Typically, most of the time, I think people are trying to get this and throw away that. All right, so in the far field, what's actually emitted that comes out of the crystal is actually the second derivative of the polarization density. And so this bump becomes this kind of wiggle. And so that's closer to what you would actually expect to see come out of the whole thing. All right. So how do you throw away the second harmonic and keep the terahertz? So as with any nonlinear process, the key is phase matching. Okay, so typically when you're generating second harmonic light efficiently, you phase match for the second harmonic generation. That's why you don't see the terahertz. Now we're going to do the opposite. We're going to try to phase match for the terahertz and not care at all about efficient second harmonic generation. Sometimes it happens, sometimes it doesn't. We don't care. All right, so the process is going to be equivalent to difference frequency generation. So what you're actually doing, so this is, and I'm not going to show this, but you can kind of, it's kind of, I think, understandable, is your initial femtosecond pulse in Fourier space has a lot of different frequency components contained within it. And we can equivalently think about this rectification process as difference frequency mixing between different frequency components of our incoming pulse. Okay, so that's sort of the way to think about the phase matching condition. So if we pick two particular frequencies that are contained within our initial pulse, omega 1 and omega 2, we need these sort of phase matching conditions. So, okay, well, this is not really a phase matching condition. This is just sort of a consequence of the mixing, that your terahertz frequency that's generated is just the difference of the two frequencies that you're mixing. Phase matching condition is really this thing that says that the wave vectors of the two incident pulses, the subtraction of those has to be equal to, or at least close to, the wave vector of the terahertz pulse. Okay? And that should be true for every frequency pair that you can find inside the pulse. So it's not just two particular ones, but you have to go through every possible pair if you want to do this right. So what you want is sort of a neat way to express this is you can just divide these two equations, and that's what this is. And then that, since these frequencies are pretty close to each other, these are the frequencies in the femtosecond pulse, we can approximate this as just the derivative of omega with respect to k, which is otherwise known as the group velocity. Okay? So we're left with, and then this thing over on the right-hand side is just the phase velocity of the terahertz radiation. It's the frequency of the terahertz divided by its wave vector. That is the phase velocity. So the condition is pretty simple, and actually you could have arrived at this conclusion thinking in a different way. It's just saying that the group velocity of the pump for efficient generation has to match the phase velocity of the terahertz. And that kind of makes sense, because if that weren't true and you had a long crystal, that would mean that the terahertz that you generate from the front part of the crystal would start propagating into the rest of the crystal. If it would have a phase velocity that's not matched with the group velocity, then at the end of the crystal, the newly generated terahertz radiation, because the terahertz radiation is generated by the envelope of the material. And that the time dependence, the propagation of the envelope is governed by the group velocity. And so at the end of the crystal, if you didn't have this matching, you would have a mismatch between the newly generated terahertz and the terahertz that was generated at the front of the crystal. And so you get destructive interference. So that's, you lose your phase match. Okay. Okay. So this is going to be accidentally true in some materials. So one approach to doing this is just sort of to look at a bunch of materials and figure out which ones satisfy this condition for the frequencies that you're using. Okay. So this is kind of a pain to do, but it's actually fruitful because there are a lot of non-inversion symmetric crystals out there. There are other criteria that you have to support, like it has to be transparent to everything, the 800 nanometers and the terahertz. I'm getting some feedback again, but I'll try maybe not to move so much. Is it the air conditioning? Oh, okay, I thought it was me. Okay. All right. So it's accidentally true in some materials, for example, zinc telluride and gallium phosphide. At 800 nanometers, this works. And then something that we do a lot in our lab is we use these weird organic crystals that I can't pronounce the proper names of, so I always use the abbreviations. So it's called DAST, OH1, DSTMS. It's got like a really long name. I can't remember. But those work. Those have phase matching when you have 1.5 micron pump wavelengths. Okay. And then you can also use the normal way that you do it. Like if you're thinking about second harmonic generation, the normal way that you're taught to do it is you use birefringence. The problem is that that oftentimes the birefringence is not sufficient. In one particular material that I know about, you can actually do it using birefringence. That's gallium selenide, and you can do that at 800 nanometers. But in most materials, the mismatch between the group velocity and the phase velocity is so big that it doesn't really matter what polarization you have. You can't really manage to do it. Yeah, and this is why I'm talking about 800 nanometers a lot, because that's where we tend to make our femtosecond pulses. Although the 1.5 microns can be generated by, say, an optical parametric amplifier, or directly in some cases, if you have a laser that lasers at that. All right, so yeah, you have to have a transparent material. You have to have cannot possess inversion symmetry. That means that sort of goes together. The second order susceptibility should be fairly high, and you want phase matching over all the terahertz frequencies in the pulse. So that usually is a limiting factor. That's actually what oftentimes causes the limited bandwidth that gets emitted from an optical rectification process, because you can't really do this, because usually, well, I think, actually I was trying to think last night if I could really prove this. I think it may be possible, but I think any material with at least all the materials I know that don't have a center of inversion symmetry have an optical phonon mode that is IR active that's actually fairly strong. And so that's the problem, is those optical phonons tend to land in the terahertz range somewhere. And so that obviously you have a problem with the absorption, the transparency, and also you get a lot of dispersion when you get close to that wavelength. So that's why you sometimes use these different crystals. Gallium phosphide is somewhat lower efficiency, but it has this low frequencies, but it has a higher frequency optical mode. So it's often used, especially for detection purposes. All right. I wanted to give a little bit of how to cheat at phase matching, since this is something that is quite useful and used a lot for high field terahertz pulse generation, at least at sort of frequencies around 1 terahertz. So you have this lithium niobate. So lithium niobate is a very nice material because you grow huge crystals of lithium niobate. It's super transparent, and you can grow grow very big, nice, defect-free crystals. It's robust. It doesn't burn easily, even if you have very high laser powers going through it. And it has a reasonably good second-order susceptibility. It's not fantastic, but it's good. What's bad about it is that the phase matching condition is very poorly satisfied. So there's mismatch by about a factor of 2 between the phase velocity and the group velocity. And the group velocity is the higher of the two. Okay, so what happens if you take just, let's assume we have like a very small beam of 800 nanometers propagating through a lithium niobate crystal. Okay, so this is our narrow pencil beam going through as a function of time. So what happens is, since the phase velocity of the terahertz is much slower than the group velocity of the 800 nanometers, the emitted terahertz has this kind of cone shape. Okay, so because the terahertz that's generated, say, over here propagates more slowly than the group velocity of the pump pulse, you get propagation in sort of a spherical, well, if you apply like a Huygens principle kind of thing, you can think of like a spherical wave. It's not really spherical. There's some weighting, of course. But you get some component that's propagated off in this direction. But the components that propagate in this direction are not able to keep up with the new generation. And so you have destructive interference along this direction of the terahertz radiation. That's why you don't have phase matching. But you do get kind of this cone of radiation in the terahertz range that's like this. And this is a 2D cut. In 3D, it would really be a literal cone. And then you can estimate the angle of this cone, this theta c, that's also related to this angle here. That's the cosine of that is the ratio of the phase velocity to the group velocity. All right, so the idea is it's similar to like if you have a duck in a pond, or you could have a motorboat in a pond, but I like ducks better. So you have like anything that's moving on the surface of water faster than the speed of surface waves on the water will generate a wake. Okay, so like a speedboat would do the same thing. The duck happens to be moving fast enough in this particular level of water in order to generate a wake as well. So basically our duck is our 800 nanometer pulse, and the water wave is our terahertz pulse. And so, yeah, so this is my sketch of this. We have the duck. It's propagating this way, and it's generating our cone of terahertz radiation. So we could, in principle, use this terahertz radiation that's generated on this cone. The problem is that the laser pulse duck can only be so intense. Okay, so at some point in lithium niobate, you will burn the lithium niobate if you have too much intensity. And so it's true that the terahertz will scale with the intensity of the pulse. At some point, though, you reach a material damage limit. So the duck is only so, heavy, basically. Otherwise it sinks, right? So that's sort of the thing. So the way to sort of, you want to amplify your terahertz on one of these branches somehow. And so the solution to do that is to get some duck friends. So you take another duck, and you tell it to swim a little bit behind the other duck, but a little bit over as well, so that you have constructive interference on this side of this wake. And so you can get a bigger wave over here. you sacrifice this side entirely, and you try to amplify this component over here. And then you get another duck and another duck, and you get basically a whole row of ducks. And ideally, you'd have a continuum of ducks here, okay? And that would generate this, and then you get amplification on this side. Okay, so how you actually do make the tilted duck row in optics is, well, the easiest way to do that, and I think the easiest conceptual way is just to use a grating. You can also use prisms. You have to use some kind of wavelength dispersion. I think it's easiest to think in terms of the grating. So normally, at least if you have a properly aligned laser, you don't have the so-called pulse front tilt. That means like your pulses that come out of the femtosecond laser should look like little pancakes flying through the air. And the pancakes should be orthogonal to the direction of propagation. If it's not, then something's wrong with the alignment of your laser. You should go fix it, right? So we start with this, but we want to now generate a tilted pulse front. And so the easy way to do that is you bounce it off of a grating, and you do like a, not the zero order reflection of the grating, but like say a first order reflection of the grating, so that the angle of incidence is not the same as the angle of reflection, and that will cause the path length for say this part to be different than the path length for this part, and so you'll end up with a tilt here. Now you also have a problem at this point because now you also have the wavelengths getting dispersed, so you have to fix that somehow. So you need actually, you need to do an imaging system where you recombine the wavelengths. So you have to actually, what you do is you image the grating onto the actual nonlinear crystal. But this is the basic idea behind how to generate a tilted pulse front. If you want more details, this is the paper to look at. So you generate, the idea is that you have your tilted pulse front. These are sort of our row of ducts, and you're generating a row of coherent terahertz radiation along this sort of line back here. All right, so if you do this kind of technique with the tilted pulse front, you can get fairly high field strengths. You can get in excess of 1 megavolt per centimeter. This is actually an old paper. I guess it's a little bit easier now to do it with somewhat higher rep rates. You again get kind of single cycle pulses that look very similar to what I showed for the photographic switches. And the spectrum is also fairly similar. You can do this in other crystals with different cutoffs and get somewhat higher frequencies as well. But the trick to getting these very high fields is actually to pay attention to the focusing quite a bit, because like I said, 1 terahertz is a 300 micron focus, and so that's actually a pretty big limitation in terms of diffraction limit. And so that's something that needs to be considered too. Okay, questions on optical rectification or ducts? Yeah, there's a question. Yeah. Well, okay, what it means is, I have some examples way back. Well, okay, so what I mean, so inversion symmetry basically just means that there is no point in the crystal in which you could perform a spatial inversion. So if you take, you define a particular point, and then you take all the atoms and you move them to the minus position of their coordinate. That's what inversion is, right? So inversion symmetry means that if something has inversion symmetry, that means there exists a point in the crystal, at least in an idealized version of the crystal that has infinite boundary conditions, where you can perform this inversion operation and you get exactly the same structure. So that if you have that, then you can prove that this second order susceptibility has to be 0. That's what I mean by that requirement. It's the same requirement as for second harmonic generation. Is that clear? Okay. Other questions? Yeah. You want to see the ducks, or do you want to see the? Okay. You don't like the ducks? Okay, fine. Yeah. Oh, right, right. Well, okay. So the idea is that if I took, yeah, it's kind of. I know these circles are. I think these circles got moved a little bit. Um, the idea, though, is that if you think about a particular moment in time, so let's consider the moment that's drawn here, where you have the tilted pulse front in this direction. Okay, so at this particular moment in time, this part of the tilted phase front is generating new terahertz radiation. Actually, well, it's all generating new terahertz radiation. You want this to constructively add with terahertz radiation that was generated at an earlier stage in the process. So if we move back a little bit, say to this point, I think so like here, so that's what that's, yeah, I don't know. I think the circles got slightly moved. I'm sorry about that. So the idea is that, yeah, you're this distance is equal to this distance, so you get it's always constructively interfering. Yeah. Well, it doesn't work over here. Over here you have nothing. Yeah, yeah, it's going to go like this. Yeah. And it will, I mean, you have a little bit of spatial walk off, of course, as well, right? Because as this is moving along, you're generating terahertz out here that is not going to end up overlapping with the terahertz it's generated here because of the spatial walk off. That's another consideration that you have to have. But yeah, yeah, it's going to propagate this way. Yeah, you're trying to match the tilt to the direction that the terahertz will go. Okay, and then oh, there's another question. I'm sorry. Yes. Well, yeah, that's kind of annoying. But you basically end up with a fairly fat beam, and then you have to go through a focusing optic procedure. You end up with sort of a big fat terahertz beam that is given by the sort of surface of the tilted pulse front that you generated, and it tends to be longer in one direction. So what you do is you try to collect that with a large numerical aperture optic, and then you relay image that to your sample. Well, typically. I mean, you could also, I guess, try to directly focus on the sample, but that doesn't work so well. So what you do is you take an off-axis parabolic mirror, and that's usually huge, like 2 inches or so, and then you focus that down, and then you relay that to another off-axis paraboloid, which then recollimates to a smaller size. Then you propagate that to the experiment, not too far, and then you refocus with another off-axis paraboloid. Yeah, that's actually the part I didn't talk about. That's all the work actually done in this paper. Oh, okay. Yeah, I think so. This was a very actually at the time it was super impressive because of the very good focusing that was done. So yes. Okay, tomorrow there'll be a talk. Maybe we'll say something about it. I hope I'm not stealing your. Oh yeah, yeah, right. That is your paper. Okay, sorry. Yeah. Okay. All right. Other questions? Yeah. Well, yeah. Ideally, you'd like more higher frequencies because that's where most of at least the phonons that I'm interested in live. Um, I'm not talking about. So there's also like you can come at it from the other side. So you can do like different frequency generations in the mid IR and try to go to low frequencies. That's essentially just difference frequency generation, just sort of extended with different crystals. Yeah, I think there's a lot of interest in going sort of between 4 and 15 terahertz. There are a couple papers that show some results in that range. Yeah, it's just sort of like you have to play a couple tricks in order to do that, but it's difficult. It's difficult. Um, for optical rectification, that's usually one of the big problems is that you have interaction between the optical modes of the crystal itself. Although in some cases that can be mitigated. Like with the organic crystals, there's some reports of generating sort of tunable radiation in this range of 5 to 15. Of course, if you go to accelerator-based sources, you obviate that problem entirely because the accelerator-based sources don't use a medium for the generation. They rely upon relativistic electrons being accelerated, and then you don't have that problem anymore. But yeah, then the problem is access. Okay, good. Okay. I'm going to not talk too much about this then. So detection, and I think it was actually in Tanaka-san's talk, you're going to talk about EO sampling, or? Okay. I mean, yeah, so that's, I mean, okay, so one key aspect, at least from our perspective, particularly though if you do terahertz spectroscopy, it's important to be able to measure the terahertz radiation. For our purposes, we're typically using the drive dynamics, so we're doing that mostly as a diagnostic to make sure we know what we're driving the sample with. But if you're doing some kind of using terahertz as a probe, it becomes extremely important to accurately measure the electric field as a function of time. Yeah, so that's what's sort of meant here by phase-sensitive detectors. I'm not going to talk about sort of incoherent detection mechanisms that aren't sensitive to the electric field versus time. They just measure like a bolometer would just be another detection mechanism, but that doesn't tell you anything about the electric field as a function of time, the phase. You can do photo switches, which I'm not going, that's sort of the inverse of the photoconductive switch, used as a detector. Electro-optic sampling, which I will talk a little bit about. And then there's ABCD detection, which is a detection mechanism relying on higher order nonlinear processes in a gas. And so typically what you're doing is all these things rely on some kind of nonlinearity that will couple terahertz and optical or near-infrared light. And I'll just breeze through EO sampling and hope that it's covered in better detail later. So the idea behind EO sampling is we're exploiting the electro-optic effect, and this is, I've had this slide for many years, and I keep forgetting to correct that. That should be multiplied by at least something. But okay, this is sort of the linear, the normal response of, this is meant to be sort of the normal response, diagonal, say, of the, it could be diagonal, it could be off diagonal, it depends on the sample. But the important thing is you have some kind of nonlinear, a second order susceptibility that is causing a change to the epsilon tensor of the light as a function of an applied electric field. Okay, so you have basically you have a crystal, you apply an electric field, and you change the speed of light for particular polarizations. Okay, that's the essential idea. And so yeah, you have a different symmetry, and then the idea behind electro-optic sampling roughly is that you come in with you have your terahertz pulse that you want to measure, you have an optical pulse that has a short envelope compared with any of the internal dynamics of the electric field. So this has to be a very short optical pulse. You send those through an electro-optic crystal. We're assuming that the propagation velocity of the group velocity of this is the same as the phase velocity of this. It's a relatively thin crystal. The idea is that from the perspective of this little optical pulse moving through the crystal, it will essentially see a constant electric field, assuming that the response function is fairly fast. You're far away from an imaginary part of the second order susceptibility. This functions as sort of an effective constant field, effective electric field that as they co-propagate. And so this optical pulse polarization, if you set up the orientation of the crystal correctly, will rotate slightly in polarization, and the angle of rotation will depend on the magnitude of the electric field. So that would be true for a linearly polarized pulse. And what you can do is sort of adopt sort of a clever scheme to make it circularly polarized in the absence of a field, and then use balanced detection to look at two orthogonal polarizations. And then you look at the difference in intensity between those two orthogonal polarizations, and that difference ends up being proportional to the electric field at the overlap position of the optical pulse and the Terrace pulse. So that's the Blitz version of EO sampling, without any real examples or depth. But is that I just want to get across the general concept. Okay. All right. So that's the end of part 2, which is about on time. I mean, I'm trying to take questions during. Are there any questions, though, on this? Anything I talked about with terahertz? Yeah. Yeah, that's. Oh, yeah, we're assuming that that's not in play, because it's we operate away from. Well, a half-wave plate would just rotate the polarization. Yeah, you can. Yeah, there. Actually, we have a paper discussing exactly this. So, the most sensitive detection involves using a quarter wave plate, but not making exactly circular polarized light, making it slightly elliptical. The problem is that if you have linear polarization at the polarization analysis, you can be very sensitive to the presence of any kind of field if you just look at the cross-polarized condition. So you have one detector look at the full field. Well, you basically stick a detector looking at the in the absence of a field, you move your you move your half wave plate and your polarizer so that you have an extinction condition, and then you let the E field, and then you do your experiments and you look for deviations from the extinction condition. The problem with that is you detect E squared. You don't detect E. So you have to have a little bit of optical bias. Yeah. I mean, this is the most straightforward to interpret version, and then the most sensitive is really doing some kind of elliptical thing, but it's not something I wanted to get too much into for this. Okay, that was a deep question. Yeah. Well, the advantage is that their nonlinear susceptibilities are much higher. The second order susceptibility is actually, I think, 2 orders of magnitude higher for those. And that's just sort of because they're sort of they're very complicated unit cells with a lot of sort of weak bonding structure inside them. And so the second order susceptibility is just way higher. So that's the reason why people use. Yeah, it's a bit funny. It's a trade-off between how efficiently you can generate the 1.5 microns and whether you could live with a slightly lower Chi2. And so I would say if you're into the reason why we use the organic crystals is a lot of our samples, we're trying to push the higher end of the frequency range. So a lot of our phonon resonances that we're interested in driving are around 3 terahertz. And there you really want to, and then the other advantage of the organic crystals is they have a higher cutoff, and we can generate higher fields at higher. But that's yeah. It would be nice to have a different to pump it at 800, but it's actually more of a question also of how you can cut the crystals, because they grow along a particular direction, and it's very difficult to get large crystals with the cut. You can actually cut them in a different way that would phase mesh them for 800. But it's basically impossible to get big enough crystals for that purpose. Okay. No other questions? Okay. Coffee break time again. Could I? Yeah, let's do it at 5 past. Come back. Yeah. It's about my limit. I actually have a course next year that is 3 hours too, and then I'm kind of like exhausted. This topic. Hi, sorry. I should have pointed it out when I first showed the paper. Yeah, of course. Yeah, that's the zoomed in version of what I was showing. I didn't want to get into this, but yeah. Yeah, no, it's exactly what you do. Yeah, yeah. And you have always the. So you, if you here, you have like an evanescent wave that's in that can sometimes be used for exciting nonlinear effects. That's actually what capillary. Well, it's an evanescent wave, so it has a certain length. So you're doing, you have to have a near surface probe. But terahertz, the wavelength is so long. That, yeah. Yeah. I'll take a tea. Does that make you happy? Okay. I mean, originally I was going to talk about just temperature increases too, but okay. Okay, I think most people are here, and it's. Am I allowed to start? Chair? Okay. Okay, so Mariano yelled at me, so I changed the title of this third part. Instead of saying detection of coherent and incoherent phonons, I said coherent and squeezed phonons because, of course, there is coherence in the squeezed phonons. They're not coherent phonons in the Glauber sense that I was discussing, but there's a certain amount of coherence there. It's not a thermal state. This is, I hate these terms, but okay. All right, so now I'm going to basically go from the terahertz. I was basically over here on this side of the electromagnetic spectrum. Now I'm going to jump over to this side, to the X-ray part. So the idea is that I'm going to only be talking about using X-rays as a probe of dynamics. There are actually some kind of possible schemes to use X-rays to drive coherent dynamics, but I don't have time to talk about this, and it's a bit sort of, there are some examples out there. I can say more about it if somebody's really curious. But I'm going to be focusing on using X-rays as a probe. And the advantage that we're going to sort of focus on is the wavelength of the X-rays. So the idea is that since X-rays have a wavelength that is comparable to the interatomic spacing, it's possible to do interferometric measurements of where the atoms are. And that is essentially answers sort of, in principle, if we know where all the atoms are as a function of time, that's all the information that we would ever dream of. And so that makes it, in some sense, kind of a nice tool for looking at structural dynamics. Yeah, so that's basically, okay, I guess I should have shown this while I was talking. But basically, you do some kind of interference, and I'll talk more about this later. I guess back here, maybe before I get away from this, there's also the photon energy that's important. And that I'll talk very briefly about. That's more relevant in X-ray, sort of what I would call spectroscopy, because these energies correspond to electronic transitions between sort of deep-lying core states of atoms and, say, the continuum. And so you can actually combine, in some cases, both the sort of diffraction measurements with that to sort of get at some non-phononic degrees of freedom that still have long-range order that couple maybe to the phonons. So that's another advantage. Okay. So I'm going to start off by just talking about short pulse X-ray sources. And I'm going to start with a very general overview and not go into detail on anything except the things that I use. Okay, so I'm not giving a comprehensive overview of short pulse X-ray sources. I don't know if Matthias, did you talk? No. Okay, you just showed. Well, yeah, but okay, you had an example of a plasma source. So in the long version of this talk, I also talk about plasma sources too. But I thought you probably did a better job. So, okay. So, and this picture is not reflective at all of a plasma source, by the way. So, but sometimes I like to come up with little cute pictures next to the things, and yeah, okay, that's what turned up in a Google search of plasma. Uh, so you have roughly, I say roughly two different categories of femtosecond X-ray sources that have been used and are used. These are more or less, I think I picked out the current ones. So you have laser-based sources. There are other ones that I'm not showing, but these are the ones that I think that are currently being used. So you have laser-produced plasmas, and so an example was Matthias's talk from last week. And another example is doing so-called high harmonic generation. So this is a very high-order nonlinear process that you do within a gas, typically. That sort of the idea is you sort of do very, very high-order harmonic generation up, several, like 25 orders or so of multiplication of the frequency of the initial pulse. So that gets you sort of what I would call VUV or soft X-rays. So these are wavelengths around 10 angstrom, well, longer than 10 angstroms. So they're not quite enough to do most diffraction experiments that you would want to do, at least not currently. And then there are, but plasma sources, of course, actually do fill that range. So this is sort of a low energy, low photon energy, and these are sort of high photon energy. This is used typically for diffraction. What I'm going to be focusing on are accelerator-based sources. And then there's basically two in use. There's slicing, which is, well, it's used in some places. It's kind of going down. We actually just closed our slicing facility a couple years ago, but we still are trying to analyze data from it, so that's why I still talk about it. And then you have X-ray free electron lasers, and I'll be focusing on these two. I wouldn't normally talk so much about slicing, but it turns out that the physics of slicing is almost the same as physics of the FEL, at least in my view. So I'll talk about both in a sense. All right, so the basic idea behind accelerator-based sources is that you have relativistic electrons that are trapped within some kind of vacuum chamber, some long vacuum chamber that is steered using strong magnets. And then in a synchrotron, that's steered in a circular orbit. And then the idea is that every time one of the magnets, or if there's any kind of acceleration of the electrons inside this vacuum chamber, you'll get an emission of a radiation cone. And since the electrons are traveling at relativistic speeds, the direction of the radiation cone is extremely forward directed, and that's a consequence of the Lorentz transformation, from the electron rest frame to the lab rest frame. That causes essentially all the radiation, or at least all the X-ray radiation, to be sort of collimated into a fairly narrow cone that has an angular width of 1 over gamma, where gamma is the relativistic factor. So it's usually on the order of several thousand for a typical synchrotron. Depends on how close the electrons are to the speed of light. So if you want to know more about just general synchrotron radiation and stuff, this is a reference of that. There's also another reference that I stole the pictures from. I'm not going to talk too much about synchrotron radiation, but the important point, though, is that you can use accelerated relativistic electrons to generate radiation in a broad range of wavelengths, including the X-rays. All right, so one of the things that at least the modern synchrotrons have developed in order to make very, very intense light, so there's always demand for more and more intensity of light, is the idea that, well, you get some light from a single bend. So you take your magnet and you bend the radiation and you get this cone of radiation. That's good for some experiments, but some experiments want more light. And so was sort of invented this scheme of using periodic magnetic structures to make the electrons wiggle back and forth, so that you get multiple you get the contribution from multiple accelerations of the electron beam in the forward of the electron beam that result in a photon emission in the forward direction. So you just basically make it bend more times, and then that results in more radiation. And so there are two different limits. I don't want to talk about the technical distinctions too much. There's this thing called wigglers and things called undulators. They both basically mean the same thing in English, at least colloquially. The technical distinction has to do with how big an angle you make the electrons go back and forth. In a wiggler, you make them wiggle more, and then you have a highly incoherent addition of the radiation. In an undulator, the wiggling is less, but then there's an overlapping between the radiation cones, and then so you get more spectrally narrow peaks coming out of it. So you get more interference. But it's important to note that these are incoherent sources, because each electron that propagates through is generating light, but it has no phase relationship with another electron in another random position within the synchrotron. So these are incoherent sources of radiation. They can be sort of treated to make them coherent, but intrinsically they have no coherence, or very limited coherence. Okay. So the key behind understanding how an FEL works is, so an FEL is a free electron laser. And in order to build a laser, you need to have some scheme of amplifying light. Okay, so now I'm gonna discuss now basically schemes. If you start off with a little bit of a pulse of light, a little bit of light at the sort of correct frequency that you want, how you would use relativistic electrons to coherently amplify that light, because that's a precondition for building a laser. All right, and we're going to do it in a completely different way than the normal lasers that you deal with based on atomic transitions. All right, so if you just think about a sort of a femtosecond pulse with full coherence, you have that's sort of the electric field, and it propagates as a function of time. So it's propagating in this direction, and this is the electric field that is transverse to the direction of propagation. All right, so what we want to do is we want to use relativistic electrons to amplify that light. All right, so the problem is if we just superimpose this light pulse on a bunch of electrons that are propagating in the same direction, we have a problem, because the electric field, so predominantly the electric field is what's going to transfer energy. The magnetic field's also there, but it's not going to end up being that important for the physics. The electric field is transverse to the direction of the velocity of the electrons. And this is a problem because it means that you don't really have very efficient energy transfer. Whoa. All right, so much for the recording. All right. I should not move so much, I guess. That's my. All right. So, so you need to, in order to have efficient energy transfer, you need to give a little bit of a kick of the electrons in the transverse direction, so that you have the dot product of the electric field, or the force on the electrons in a classic, it's relativistic, but it's not quantum. You have essentially a force on the on the electrons. You need that dot product to be non-zero, and so you need to kick it a little bit. And the way you do that, and you still keep it roughly propagating in the same direction, is you pop it through an undulator. So that will make the average velocity along this direction still close to the speed of light, but you'll have this little transverse kick that allows you to have some energy transfer between the light field and the electrons. All right, so this is my carefully made animation showing this energy transfer process. So this is meant to be an electron inside our accelerator, and this is again our electric field of the laser pulse. The color of the electron is meant to indicate its energy. Okay, so if you see it turn blue, that means it's getting energy. If you see it turn red, that means it's losing energy. All right, and so in this case, I've set everything up so that there's a resonance condition that you have to meet between the periodicity of the undulator and the wavelength of the field to make it so that the force, so the minus QE dotted with the velocity vector of the electron is always going to be positive. And so that will mean that this will gain energy at all points within. And so I just wanted to show this animation of how that actually works. It's a little bit, goes a little bit fast. All right, so just do it a couple times. So you'll notice that one key aspect is that, of course, the electron doesn't go as fast as the light because it can't, right? It's not only is it's a massive particle, so it can't quite get there, but also it's having to go through this undulation motion, which also prevents it from going that fast. So the resonance condition is that every time you go through one period of the undulator, you slip exactly one cycle of the light. And that's the way you maintain this resonance condition to make sure that the thing turns blue. And it doesn't just oscillate between blue and red. All right, and then you can do the opposite. So for another electron that is in a different place with respect to the phase of the electric field. So this is in the opposite situation where it's set up so that this dot product will always be negative or equal to 0 in some cases. And then you have the same kind of thing. But it turns red because the force is always acting against it. All right, so you have the situation where some electrons, so if you have this interaction of the light field with these undulating electrons, so the interaction between the light field on the influence of the light field on the electron dynamics is to slow down or to redshift certain electrons and to blue shift other electrons depending on their phase relationship with the light field. And so what happens is if you have a long enough undulator and this propagates over a long period of time, the electrons will start to bunch up. So the slow ones will slow to a certain point, the fast ones will speed up to a certain point, and you'll get this modulation of the electron beam as a function of position. And this actually has a positive feedback effect because it turns out that the radiation emitted by these bunched electrons will be at the same frequency of the light that caused them to bunch, and it will constructively interfere with that. And so you get kind of a runaway amplification of the whole process. So this leads to the so-called lasing of the free electron laser. So this is a sort of a classical relativistic mechanism for lasing that doesn't actually involve atomic transitions. So it's kind of interesting, a counterexample if you think that lasers are always involve quantum mechanics. It's not necessarily, well, you can of course use quantum mechanics to describe it, but you don't need to. So initially, what I sort of described was a seated FEL. Of course, you can also operate it like with a normal laser. You can sort of use a noise seated, not really seated at all, just self-amplified spontaneous emission. So it's not really, I shouldn't say seated by noise, but it's sort of unseated case. And this is sort of most of the current sources that are used run off self-amplified spontaneous emission. Okay, questions about the free electron laser? Yeah. Well, it depends on how narrowly you define stimulated emission. I mean, if you decide that it has to be an atomic transition, then I guess it wouldn't be. But it is. I mean, the fact is that the key aspect of the laser action is that you have this positive feedback between the medium and the radiation field. So, I mean, if you want to not call that stimulated emission, you can, but it has the same effect in the end. So it is at least conventionally called a laser. I think I read somewhere that someone did have like a quantum theory of the FEL, but I did not understand the paper. So, but so maybe there is a way to make it unified. But okay, actually, I forgot I had some more slides on this. So yeah, the basic idea is you have this kind of situation where this is sort of before the bunching happens. You have this incoherent addition, and so your power is basically proportional to the number of electrons. And then after the bunching, it's proportional to the square of the number of electrons because you have the addition of the coherent addition. And since the number of electrons is ordered 10 to the 9, this is a big difference, right? So 10 to the 9 between these two. So that's why free electron lasers are a relatively big deal. So we used to do all our experiments with slicing source, and now we shift more to FELs, largely because of this 10 to the 9 factor. Yeah, then you have a typical saturation curve. Well, it's typical. It's a calculated one. It's a cartoon, really. So the idea is that you start with sort of, this is your noise, sort of the amplified, self-amplified emission starts here, and then this is the amplification stage. At this point, you have a saturation because you, at some point, overbunch the electrons, and then you can't have more coherent addition. So the result, though, is you have these coherent, short X-ray pulses with at least features that are less than 10 femtoseconds. And then, yeah, so those are some stats. Are they totally current? Probably. Yeah, they're close enough. So it's sort of, you get to about 10 to the 12 photons per pulse, but it's very collimated. That's the one advantage. So this is actually this is mostly useful radiation for your experiments because you have this microradian divergence or so. Brilliance numbers are through the roof, and it's also spatially coherent, which is a big advantage. So high harmonic generated sources are also spatially coherent, but they're not able to access the wavelength range. And yeah, stability is poor. As an editorial comment for someone who's used this a lot, compared to a laser. There are actually Fermi has a seeded free electron laser, which actually has much better stability. So that's actually one of the key differences. But it operates only in the sort of UV and soft X-ray range. All right. Okay. Last chance to talk about, no, it's not your last chance to talk about sources, but it's a good time to talk about sources if you have questions, more questions. Okay, so this is going to be a quick review of the basic principles of X-ray scattering. I may skip over some things in the interest of time, but I wanted to give kind of at least an overview of what's going on. Okay, so if you sort of look at basic textbooks on matter-light interaction, you can write down the Hamiltonian for a free particle in a non-relativistic approximation that has a mass m and charge q, and it would be this. This is P minus QA over C, so this is the vector field. You can expand depending on, you can expand this out. I didn't pick a particular gauge. Typically people do at some point. But you have basically a kinetic energy term. You have this term involving A dot P, which is typically what we're working with optics. So these refer to, for example, some kind of inelastic scattering, for example. And then you have, but what's more important for the X-ray stuff that I'm going to be talking about is the last term that doesn't involve A dot P. It involves the amplitude of A squared. So this is just, A is just dependent on the field. But it does depend on Q squared. So Q is the charge of the electron, and M is the mass of the electron. And this is referred to as Thomson scattering. All right, so that is going to be the main focus of what I'm talking about. I'm not going to be talking there. I'm briefly going to mention some effects that have to do with this. These typically lead to higher order corrections in the response of the X-rays. This is sort of the main player in terms of X-ray diffraction, typically. And the reason is because, and sort of this also points at one of the advantages, I should mention, of X-ray diffraction, is that this is sort of why it's typically said that the X-rays are looking basically at the electron density. So they look at the electrons and not the nuclei because of the factor of m here. So basically you have this 1 over m factor, which makes the electrons much more important than the nuclei because of the mass difference. And but otherwise, you just have this charge, and you don't have any details of, like, for example, the detailed physics of the bonding or something. It's really just looking at the charge density. All right, so I'm going to talk only about systems with true long-range order. You can generalize some of the stuff that I talk about to quasi-crystals or incommensurate superlattices, but I don't want to talk about that because it gets complicated. You essentially, though, have a unit cell, and then you basically repeat that unit cell using particular translation vectors, which I'm going to call T, bold T, to build the crystal from the unit cell. Okay, so that's hopefully pretty clear so far, so I'm not going to deal with that a lot. All right, so to a fairly good approximation, your intensity that you measure with X-ray diffraction is given by the so-called scattering factor F squared. Okay, so this is sort of the magnitude of the electric field goes as the F, and then we're taking the magnitude squared because we typically can only measure the intensity. This F, it can be broken down again to a fairly good approximation, at least for reasonably heavy atoms, as a sum of atomic scattering factors. That's these F. Well, these are scattering factors for each unit cell, and these are phase factors that basically take care of the fact that you have superposition between different electric field oscillations. All right, so you have, in principle, you can split these form factors. This would be atomic form factor, sorry, and this would be a different way of writing it, where you think about the unit cell as one scattering unit by itself that has this relationship. So these are essentially the atoms. This is a sum over the atoms within a unit cell. So in this example drawn here, there are 3 atoms per unit cell. So each of those would have an atomic scattering factor, which can be a complex number. And then we're adding up the contributions of each of these atoms within the unit cell, taking into account basically phase delay factors from the scattering process. So that's what that is. You can lump all that together into something called a crystal, a unit cell structure factor. And then you can represent the interference between different unit cells by this e to the I q dot t. So t, remember, is the translation vector that says which unit cell you're in relative to some arbitrary origin. And q here is, I don't know if I have somehow missed defining q in the slide, which is kind of unfortunate. Q is the, q is a vector that is called the momentum transfer of the system. Okay, so this is called the momentum transfer. All right, so it essentially is giving you so this is the final momentum of the photon. This is the initial momentum of the photon, so that's why you call it the momentum transfer. It's the momentum that the X-rays give up in the scattering process. And so that's what this Q, I should have mentioned that at the beginning, I don't quite know why it wasn't there. That's this momentum transfer thing that comes out all over the place. All right, so right, so the main result is that if you have a large crystal and many unit cells, you will get extremely strong peaks whenever the dot product of Q and T is some multiple of 2 pi. Okay, so that's the so-called Bragg condition for positive interference, and that's, you can see clearly from this, because if Q dot T is some multiple of 2 pi, then this e to the I is e to the I 2 pi n, so that's just going to be 1, And so we're just adding together contributions in phase from every unit cell inside the crystal. And so you get a huge peak typically under those conditions. You typically call values of Q that satisfy these conditions. These have a special name. These are called reciprocal lattice vectors. And so it's basically so you solve this kind of condition and you get these vectors G. It turns out that you can show that these G vectors are really just a superposition of three basis vectors in so-called reciprocal space where these are integers. Okay, so H, K, and L are particular integers. All right, so you have this concept of reciprocal space where these are direct space. These are actually showing you where your unit cells are. You can think also in reciprocal space where you think where these allowed G vectors, these reciprocal lattice vectors, would sit. And they make a lattice that looks similar to the direct space lattice vector, but everything's a little bit upside down, so that's why it's called reciprocal space. I don't want to go into the that's a very hand-wavy way to look at it, but that's the level that you're getting here, sorry. Okay, so the important thing I wanted to get at was this concept of the Ewald sphere, which I'm going to represent in 2 dimensions, so it's going to be an Ewald circle. So the idea is that I'm drawing here reciprocal space, and so the idea is that whenever these lines cross, that's going to be an allowed reciprocal lattice vector. So this is a reciprocal lattice vector, this is a reciprocal lattice vector, this. This is 0. That's also a valid reciprocal lattice vector. It's kind of a trivial one. But this is like the 0 condition. And the idea is that the idea of the Ewald sphere concept is this is kind of a graphical way to sort of figure out where you're going to have, or where you're looking in reciprocal space when you do an X-ray diffraction measurement. And the easiest way to explain that is to think about, well, what are the conditions in which I'd see these bright Bragg peaks? So the way you do it is you draw your reciprocal lattice in this kind of, say, representation where you show basically all the different points in reciprocal space where there are Bragg peaks. And then you define an origin. And then what you do is you take your incident wave vector. So this is 2 pi over lambda in magnitude, and the direction is set by the orientation of the crystal with respect to the X-rays that are coming in. Okay, so this orientation is not arbitrary. It's defined by the actual experiment that you're doing. And you put the tip of your vector at 0, 0, and then you basically slide it so that you can look and see where this arrow starts. And then what you do is you draw a circle with a constant radius that goes through 0 all around reciprocal space. If this were a 3-dimensional representation, this would be a sphere, the surface of a sphere. 2-dimensional representation is a circle. And the idea is that these different points on the sphere/circle are giving you where you're looking at reciprocal space when you look at a particular direction from the crystal. So in this example that I've drawn here, I've set it up so that this circle will intercept this reciprocal lattice point over here. So that means that you will have diffraction based on this reciprocal lattice point, and the way you predict which direction that the X-rays are going to come out from that response is equivalent to the direction of this KF vector that you draw from where KI starts over here. And so this gives you essentially the orientation of the X-rays that come out. You don't need to look at Bragg peaks. You can also look elsewhere. Then you see things that are between the Bragg peaks called diffuse scattering. That's something that Mariano will talk about on Thursday. But that's the basic idea that you can look at certain cuts of this 3-dimensional reciprocal space, but you're only, for one given measurement, you were actually making a lower dimensional cut through the surface than the full 3 dimensions. So in this case, well, this is a 2-dimensional crystal. You'll notice that the cut that I make is 1-dimensional. If I had a 3-dimensional crystal, I'd still only be able to make a 2-dimensional cut. And in order to get a full mapping of reciprocal space, you need to do a bunch of measurements where you change either the wavelength or the orientation of the crystal. All right. Yeah, so if you wanted to just find the average structure, which is typical diffraction measurement, the idea is you somehow change this incoming K vector to move around this Ewald sphere and figure out all the places where you have intersections with reciprocal lattice points. Then you can map out exactly which of these points in reciprocal space are actual allowed reciprocal lattice points, and then you can sort of figure out from that the structure. And I don't want to go into the details of that, but that's the basic idea. All right. Yeah, and then, okay, so you have this concept also of systematic absences. So some of them you will look for, but they won't be there, and that indicates typically an additional symmetry in the system. All right, and it's actually a fairly complicated set of nonlinear equations that you have to solve, and then sometimes you need tricks in order to solve ambiguities, because those ambiguities arise from the fact that you're measuring intensity and you don't have full information about the scattered field. But I won't get into that too much. All right, so time resolved. So I spent last 15 minutes talking about non-time resolved X-ray diffraction. So we have to bring it back now to time resolved. So in principle, you could think it's pretty easy. You just use short pulses of X-rays. So you take your FEL, you bring your thing there, and then you can measure the full structure, and you know where every atom is at all times. It's really easy, right? So, okay, one problem is that, of course, if you have a short pulse of X-rays, that means you have somewhat broadband, and so that will fuzz out the Ewald sphere. That's not actually a major problem, but that is a limitation to the Q resolution. If you thought about doing super short pulses, it would possibly become an issue. But it's not really that simple. So the problem is that you need to combine this with a pump to do a time-resolved experiment to trigger the dynamics. Because remember, if you want to look at a coherent phonon, you have to define an ensemble that has an unambiguous time 0. And so you should have a pump if you want to do these kinds of measurements. Or you need some kind of reference in order to look at the coherence. So it's very difficult to keep identical pump conditions when you're moving around in reciprocal space, because typically that involves rotating your crystal around, so that's difficult. You also have penetration depth issues. Usually X-rays penetrate more deeply than other light. You need to somehow make sure that the experiment is somehow repeatable. You either have to deal with a heat load issue, which can be an issue for both the X-rays and for the laser, or you have to devise some clever way of replacing your samples. So there are a lot of sort of issues. And you also need to typically focus on one particular area of reciprocal space. So actually, back when I used to sort of be the liaison for slicing experiments at the SLS, and it's surprising the number of people who just sort of thought that you could just sort of measure everything about the atomic positions without thinking about it beforehand. You just sort of plug it in, and then you'll have like where every atom is as a function of time. It doesn't really work like that. You have to actually usually sort of think about your experiment quite a bit beforehand. All right, so I wanted to show some examples of things that actually happen with reference to coherent phonons. So K = 0 optical phonons are probably the easiest to explain, at least for me. The idea is essentially that you have, so this is a very simple lattice consisting of a basis set of two different atoms. And the idea behind K = 0 optical phonons is that you can just represent that as these are relative motions of these two atoms with respect to each other that's identical in every unit cell. And so what you can think in terms of X-ray diffraction is you can think of this as interference between two sublattices. And the interference between two sublattices will result in variations of the intensity at particular Bragg peaks. What it does not do is it does not produce anything away from the Bragg peak. So if you want to see these K = 0 optical phonons, you have to look at the intensity of these Bragg peaks as a function of time. So yeah, you sum that over unit cells, you have a crystal structure factor, and for these K = 0 coherent optical modes, your RJs are essentially, this is the equilibrium position, this is the deviation. That's the same independent of every unit cell. And so you can basically think of it as a time-dependent crystal structure factor, and your mission is to figure out the magnitude of that, or the nature of that crystal structure factor. All right, so this is an old experiment that we did a long time ago, but it's a nice illustration of some of the techniques that you use. So this is a crystal of bismuth, which is sort of basically what I showed before with these two different atoms in the unit cell. And there's a mode where they're moving against each other. And you can do these sort of, what we did is we did a lot of these sort of grazing incidence measurements to deal with the pump probe penetration depth. So the X-rays typically will go further than the pump. And so, but what you can do is you can, if you go at a very glancing angle, you can make the X-rays penetration depth equal to that of the pump if you're very careful with this kind of geometry. And then what you see though in the experiment though, this is the oscillations in the crystal structure factor as a function of time, and these can be mapped one-to-one onto changes in the expectation value of the Q as a function of time. And so in our sort of sloppy definition of a coherent phonon, we have a measurement of the expectation value of Q as a function of time. We see it wiggles, coherent phonon, victory, right? That's basically there. But the advantage of this is you can extract from this a quantitative measure of how much the atoms are moving. So that's the advantage of this over say, optical reflectivity as a measurement, because you can exactly calculate the relationship between the crystal structure factor and the amplitude. So this has been done in a lot of different systems. You can do measurements of many different Bragg peaks to figure out the dynamics of somewhat more complicated systems. So this was the next step up. Tellurium, that's a crystal with 3 basis atoms, and you can measure multiple peaks, and then you can solve the nonlinear equations to actually figure out what each normal mode at k equals 0 is doing. So these are all the different normal modes at k equals 0. And these are measurements of the expectation value of that. It doesn't have the little angles there, but that's what that means. So you see in this case, there's basically only one mode that's excited and the other ones are within the noise. This is an increase in the disorder of the system. So this is a signature of basically heating of the sample. This would be incoherent phonon population. And I think everyone agrees that should be called incoherent. Yeah. Mariana's happy with that. You can also look at sort of higher symmetry kinds of modes. It's a little bit more difficult, but it's also possible to do. There are no real firm limitations on exactly what the capabilities are looking at these k equals 0 phonon modes. And then typically these are limited by the amplitude that you get is typically limited by the damage from electron. Because these are all examples. I should point out that these are all examples of indirect excitation, where you're driving the phonon dynamics by exciting electronic states, and then these electronic states couple to a displacement of the potential energy, which is why you see this. They're long-lived excitations, which makes it mathematically displacive, and so that's why it shows up as a displacement and an oscillation around a new minimum. That's actually not the case here. Here you're exciting via short-lived electronic states, and so here you have an impulsive mathematical form. So you see a sine wave kind of motion. This was a very difficult experiment, I have to say, but it worked. All right, then okay, that's the wiggles. Okay. You can also look at coherent acoustic modes. I think we have an upper bound. I have to look. It's been 8 years since I wrote that paper, so I don't remember. But I think it's in the paper. There's a lifetime estimate there anyway. Okay, so that was k equals 0 optical modes. Actually, I'm mixing up k and q a lot. But okay, so now I'm calling them low Q acoustic modes. So this is not looking at the optical branch anymore. So how does the acoustic branch figure into X-ray diffraction? Okay, there are different ways to think about it. One important consideration is that you have to think about the time scale that you would expect. And that time scale is typically given by the size of the probed volume, sort of linear dimension divided by the speed of sound, because that's kind of the propagation velocity, the group velocity for acoustic modes. So typically we're talking about roughly 25 picoseconds. So it's somewhat slower dynamics on the typical kinds of scales that we're doing these experiments on. I just wanted to quickly talk about at least how that shows up in an experiment. This is an example of that, where you're using thermal excitation to launch coherent acoustic modes from the surface of a crystal. And so we don't have like an ablating layer or anything. This is just raw heating of the near surface region of the crystal. So we have a laser come in, heats it up quickly, and then we see the response as far as the lattice. So this is the deposition energy. It's somewhat exponential. So we're going to approximate this heating as an instantaneous expansive stress. So the expansion could come from anharmonic contributions, could also come from like a Graniason parameter or whatever. The idea, though, is you have this sudden stress that gets developed, and then that causes a coherent strain wave that starts from the surface and propagates in. So I think there have been examples of this kind of thing before. Okay. So, but this is sort of the strain as a function of distance, and then you get this sort of discontinuity in the strain that propagates with the velocity of sound. And in X-ray diffraction, there are different ways to think about this. One way to think about this is you can see interference between the surface of the crystal. So this is at 0 depth. That's the surface of the crystal. And this discontinuity essentially gives you a border between two regions of the crystal that have a different lattice spacing. And you get interference also from this and from this interface between these two crystals. And that results in this sort of fringing pattern that develops as a function of time, because this is moving as a function of time, and so the spacing of the fringes will change also with time. So this is angle that you are deviating from the Bragg condition, and this is time in seconds. I don't know why it's in seconds, but okay. All right, but it's yeah. So this is from Aaron Lindenberg's PhD thesis, with a graduate student with me back in Berkeley. So if you take certain like projections of this along different fixed angles, you see essentially different frequencies. And another way to interpret this is you're looking in different points in reciprocal space. And so you're seeing different dynamics corresponding to different phonon modes that contribute as a function of where you're looking in reciprocal space. So if you look further away from the Bragg condition, you're looking at higher wave vector modes, and you see faster oscillations. But this is a typical signature of what you would see with coherent low Q acoustic modes. You'd see basically the tails of the Bragg peak start to develop these oscillatory features. Okay, so that's that only happens when the tail is sort of, there's a significant tail from the raw Bragg peak overlapping the phonon of interest. If you look at very high wave vectors, where you're far away from this tail, then you have a somewhat different situation. So Mariano will talk a little bit about, I think, about that situation. You talk about static diffuse scattering at all? Or, okay, all right. So you see contributions far away from the Bragg peaks is in the form of a small intensity. But at the Bragg peak, what you see is a reduction of the intensity. And this is a bit overcomplicated for what I want to show. What it's trying to show is this is like a phasor representation of how you do the addition over all the structure factors from the unit cells. So the black is showing like a perfect non-disordered crystal. So you'd get, this would be essentially the electric field of the scattering. And the magnitude of the intensity you'd measure in this perfect crystal would be proportional to the magnitude of from here to here squared. And if you disorder with respect to one coordinate, if the coordinate has a very high wave vector, a very high periodicity, you get this sort of periodic contribution to these structure factors that in the end make it point along basically the same direction. So you don't see a lot of change in the position of the Bragg peak, but what you see is an effective reduction of the magnitude of the Bragg peak. So this is what's known as the Debye-Waller factor. So it just means that if you have a population of high wave vector modes, and actually that applies also for optical modes, not only acoustic modes, you get a small reduction of the X-ray intensity at the Bragg peak. But this important thing that I wanted to note is that this is a reduction by the amplitude of the phonon squared. Okay, so in this case, U naught is the amplitude of the phonon coordinate. Q is our momentum transfer. So I'm sorry, this is a collision of variables. Here, Q is the momentum transfer, and U naught is the magnitude of the. But anyway, well, no matter which you look at it, it's still squared, so it doesn't really matter. All right, so so you can see with this kind of thing phonon squeezing. So if we somehow make, did I skip something? Okay, so we go back to this phonon squeezing idea, where we remember if we suddenly change, we figure out a way to suddenly change the frequency of a mode, that'll induce changes, time-dependent changes in the expectation value of the coordinate. Here I went back to Q, sorry about that, squared. But yeah, you can pretend that that's the same Q. But here we have an experimental handle that actually measures this Q, this square of the coordinate. All right, so how do we actually do that? So in bismuth, it turns out that if you strongly electronically excite the system, you actually do have a change of the frequencies of at least some of the modes. So this is a calculation at two different electronic excitation levels. So this is ground state, red is ground state, and the blue is the dashed blue is the, with 1% of the electrons from one band promoted to the conduction band. You see changes depending on where you are looking in the dispersion level. So the optical phonons have are more strongly influenced, but the acoustic modes near the zone edge are also influenced. You get generally, though, it either doesn't change much at all or it decreases the frequency. So that's exactly the kind of thing that I showed here, where you have this change there. All right. So you can actually do this measurement. Mariana will show a much nicer, clean version of this, where you look elsewhere in reciprocal space and you see an increase in the scattering intensity. But if you look at the Bragg peak, you see a decrease because of the Debye-Waller factor. So this is raw data. This is where the laser hits. And then you see a sudden decrease in the intensity of the Bragg peak, and that's due to this Debye-Waller factor. And then it oscillates once, and then it slowly starts to increase. You can relate that directly to the sort of mean square displacement of the atomic coordinate. So you just do this. It turns out that this particular reflection is chosen so it doesn't have sensitivity to any of the coherent phonons that could exist in the crystal. And then if you actually do a model of what the contributions to all the different phonon modes that would contribute based on the DFT, we get actually fairly nice agreement with the experiment. And so you see in this case not so many oscillations because many different phonon modes are contributing at the same time. And what Mariana will show is if you look elsewhere in reciprocal space, you can actually separate out the different contributions because there shows up as a positive contribution that depend on where you're looking in reciprocal space. All right. Okay. Well, okay. So when is the official? So lunch is at 12:30. When am I supposed to shut up? Because now I would give the more current. Yeah, okay. So I could do 10 minutes, and then we do 10 minutes of possible questions. Okay. All right. All right, so I just wanted to give a couple examples using with coherent stuff measured by terahertz and X-rays. Well, the first one is the only one actually involving terahertz. The other one I picked up because I just like it. This is going to use a little bit of a trick that I kind of alluded to before but didn't talk about too much. What this first example is going to be a slight modification of X-ray diffraction where we don't operate away from an edge, we actually go close to an absorption edge. And so what we can do is when you go close to one of these core level absorption edges, so this, what I mean by this is a transition between a tightly bound core state of the atoms, one of the atoms inside the crystal, with an unoccupied state near the Fermi energy. And so X-rays have enough energy to do that kind of thing. If you can do that simultaneously to doing X-ray diffraction, and that allows you to get enhanced sensitivity to certain things that are not just the Fourier transform of the electron density. So you get essentially a contribution to the elastic scattering factor modified by interaction with an intermediate state. And if you're at, for example, the L edges of magnetic transition metals, then you can get an enhancement to magnetic order. But and you can also, in some cases, get enhancement to orbital order. And so these are some examples from a colleague of mine who does this quite a bit, where you see this is a function of the energy, and this is the diffracted X-ray intensity. So you see that the diffracted X-ray intensity, this is maintaining the Bragg condition, is strongly dependent on the energy when you're close to one of these resonances. And so part of the response will be due to some non-structural component of the long-range order. All right, so this is actually it's still a fairly old example, but I thought it was a nice illustration of doing this in terbium manganite. So the idea here is terbium manganite is a multiferroic crystal. So what that means is that in very low temperatures, it has a phase where you have an ordered magnetic structure of the there's sort of free spins sitting on the uncompensated spins sitting on the manganese sites. They order in kind of sort of a spiral kind of pattern. That's an antiferromagnetic order, and that antiferromagnetic spin order induces a very small lattice displacement of the oxygen atoms, primarily, that induces small ferroelectric polarization. And so this is a case of an induced multiferroic where you have a strong, the actual magnetic order is what is actually causing this interaction. So I wanted to point this out because if you look in the terahertz range and you look at the spectrum, there are resonances that have been identified as electric dipole active resonances that have to do with modifications to this magnetic structure. So what these correspond to are so-called electromagnons, which are essentially, you can think of them as hybrid excitations of the magnetism and the lattice, where essentially the magnetism is using a little bit of hybridization with the phonon system to get some electric dipole activity. Because normally the magnetic system would only care about the magnetic dipole interaction. So the idea is that what was interesting is there was a paper published almost 10 years ago now that said that if you take a very intense terahertz pulse and you excite, this is a theoretical paper, if you take a very intense terahertz pulse and you excite this upper frequency electromagnon, you can in some cases, if you go to very high fields, get a reversal of the orientation of the spins, and that will cause a reversal of the ferroelectric polarization. And so we were interested in seeing whether this was even feasible or even possible to measure something in that direction. So this is an experiment. This was done at LCLS, again several years ago, but I think it's still a nice illustrative example of this, where you do essentially looking at a Bragg peak. This is not a structural peak, though. This is actually a peak that only comes from the magnetic degrees of freedom. And you can see that experimentally by looking at the polarization relationship between the incoming light and the outgoing light. The polarization is rotated by 90 degrees, and that's a signature that you have a magnetic interaction that responds to that. So the idea behind the experiment is we measure the intensity of this peak as a function of delay time between an X-ray and terahertz, and then we use that to track how the spins reorient themselves in response to this electric field. And so if you actually do the experiment, you get this is a sample of the data. So this is showing at 13 Kelvin. These are both at 13 Kelvin. This is just opposite polarities. These are different driving fields with opposite polarity. So you can see the red is showing the terahertz electric field, and you see the response of the spin system comes with a bit of a delay. And then if you reverse, everything sort of reverses more or less. And then if you heat the system up, so it's not in this multiferroic phase where you don't have this electromagnon anymore, you don't really see much of anything. You maybe see a slight decrease, but you don't see any of this coherent response anymore. So that's an example of how you could look at, use terahertz to resonantly drive. That's an example of resonant excitation using direct methods and seeing it with X-rays. Second example, okay, 5 minutes to talk about something that I often spend over half an hour on, but that's okay. I'll just give you an overview. Yeah, I shortened it down, so don't worry. This is on the ultra-fast Einstein to Haws effect, which is a fairly recent paper we published early this year. This has nothing to do with terahertz, but this is a nice illustration of using X-rays to very sensitively and selectively look at a particular coherent phonon. All right, so the idea, if you remember from back in your bachelor physics days, that's not a good, no. When you were doing your Bachelor of Science degree, they should change that actually, but okay. It's another, like, this is going on my list with coherent phonon actually. So you have the classic Einstein to Haws experiment, which is sort of like one of the few experiments Einstein was ever actually directly involved with. Was also done wrong, but you have the idea is you have a rod of ferromagnetic material, and we're embedding it into a solenoid. And initially, we have the current running through the solenoid, and we're magnetizing this rod like this. And let's assume everything's static under these circumstances. The idea is that we reverse the current in the solenoid, and then we cause the magnetization to reverse. And the crux of the Einstein to Haws effect is you actually can observe a small mechanical torque on the system that's necessary to conserve angular momentum. So if this wire had no spring constant, it would just keep rotating. Typically, the experiment is actually done with a torsion pendulum, so you actually just see a small response. It's a very difficult experiment to do, actually, I have to say. Every time I've seen someone try to do a demonstration experiment, they're looking at some artifact. But it's a real effect, though. So we're interested in how this happens dynamically. And I'm going to kind of breeze through some of the fine points because I have 5 minutes. The idea, though, is that if we assume that we can somehow get the magnetization to change arbitrarily fast and in a spatially uniform way, this is a big if. I'll explain how this happens in a minute. And then we assume that the change in a local area of our cylinder only acts locally in force on its surroundings. There are no long-range forces from the magnetization change. Then we can sort of represent this the stress inside the crystal in a continuum model as this kind of off-diagonal stress tensor. So those of you versed in continuum mechanics may start to dig out a crucifix or something against this off-diagonal stress tensor, because this is typically not allowed because it doesn't conserve angular momentum. But that's what we're trying to do, right? We're trying to model a transfer of angular momentum from the spin system into the lattice. And so as long as this doesn't exist for a long time, we're actually good. This is representing the transfer of angular momentum. All right, so the idea, though, is that this kind of uniform stress tensor will only result on a force that acts on the outer surface of our cylinder. And so there will be no force on the atoms inside the cylinder, only on the outside. So we have a force density that's non-zero only at the surfaces, which essentially, if you look on an atomic scale, you think about this force on the outer layer, that results in a transverse wave as time propagates. So that's a transverse acoustic phonon, coherent phonon. All right, transverse displacement wave. So how do you actually cause the magnetization to change quickly? This is the part I'm going to gloss over. There's this phenomenon called ultrafast demagnetization. If you take like an iron or cobalt kind of 3D metallic ferromagnet and you whack it really hard with an 800 nanometer or any kind of wavelength laser pulse, you cause like a heating of the electronic system, which ends up being accompanied by a very fast change in the magnetization. And this change in the magnetization happens on a time scale of about 10 to 30 femtoseconds. It's been confirmed by multiple measurements. And there's been a long-standing debate on where the angular momentum goes. Because people didn't initially understand why it would drop how it could drop that fast. And one of the big questions was, how does angular momentum go somewhere else on that time scale? And so there's been a lot of talk, maybe orbitals, but that was sort of argued against with experiments, the electromagnetic field. There's theory and experiments that suggest that that's not relevant. There are two sort of remaining surviving explanations. One, it has to do with sort of a spin transport. The idea is that the reason why the magnetization drops quickly is because the spins go somewhere else outside the pump region. And that's sometimes supported by experiments and sometimes not, depending on the geometry. But the one remaining thing is the lattice or the phonons. And so if it goes to the lattice or phonons, one way in which we could see the angular momentum transfer is by trying to see signatures of this transverse coherent acoustic wave that I was describing before. Because if you have near the surface of a quickly demagnetized system, that should result in a transverse acoustic wave being propagating from the surface in. All right, so this is our sample. So we're dealing with an iron sample with some interfaces that I'm not going to get into, but the idea is we're looking at evidence for a transverse acoustic wave launching from this interface and from this interface, going propagating toward the center. And the way we do that is we look at a certain cut in reciprocal space. So this is our detector, and we're looking at a particular cut in a reciprocal space that's going to be sensitive to the components of that coherent phonon. And the way we do it is we do a clever trick where we're doing the experiment over and over again with a random initial polarity of the magnetic field, because one of the signatures of one of the characteristics of the transverse acoustic wave is that its direction of displacement will depend on the direction of the initial magnetization, because the angular momentum will depend on the direction of the initial magnetization. So that means that the actual lattice motion and the phase of the response that we see will flip by 180 degrees if we reverse the initial magnetization. So we split the data into even and odd effects. The even effects contain all the boring stuff like heat and magnetostriction. Well, okay, maybe I shouldn't say it's boring. Sorry. I remember there are a lot of posters about magnetostriction out there. But the novel effect is this Einstein to Haws effect transverse strain, which would show up as an odd contribution. So this is, just to be quick, this is the experiment on the left and the simulation on the right of what you would expect. So this is the even contributions. So this is the heat and magnetostriction contributions. It's fairly good agreement. There's a small discrepancy in the overall shape of the background that has to do with the fact that the simulation doesn't properly model the incoherent phonon populations. And this is the odd contribution. Of course, noisier in the experiment because it's a much weaker effect, but it's showing the evidence of these oscillations that correspond to this transverse wave. All right, so that's okay. I'm only a few minutes over. Okay, so that's basically where I wanted to end up. The main things, I mean, you probably didn't quite get the two last examples, but the main things I wanted you to get across was this idea that that you can see coherent optical phonons. You can also see small or large acoustic phonons or optical phonons. You just have to look in different places and look for different effects. Changes into Bi-Waller factor can be very important. And also one of the advantages that's shown by the Einstein to Haws experiment is that you can actually, the fact that you can look specifically at different points in reciprocal space is a huge advantage to actually identifying these effects and separating them from others. All right, so with that, happy to take questions. It takes 5 minutes to walk to lunch, so 10 minutes probably. Well, so our physics interest is in looking more deeply at nonlinear effects and phase transitions. So that's typically what we focus on. So we look, so I mean, I was always talking about you have this nice harmonic oscillator. So we're doing a lot of measurements on systems close to phase transitions where that's not the case, where you have, it's more correctly described as like a double well or maybe even a triple well, potential. And we're interested in these anharmonic terms that will also cause interactions between different modes. So that's sort of our current focus of research, is using these techniques to generate very large amplitude coherent phonons, with the idea that when we reach very large amplitudes, we'll start to see deviations from the harmonic response. So either by looking at coupling to other phonon modes, or looking at the phonon mode dynamics themselves and looking for evidence of other frequencies or non-sinusoidal kind of behavior, or looking at other degrees of freedom like electronic states, like driving electronic phase transitions, and looking at that by driving very high amplitude coherent modes. But that's sort of like this little bit this nonlinear phononic stuff, which is kind of this indirect way of doing excitations, which is also something that we're looking into. But that's I think where at least our current interest is. And also, well, I mean, the Einstein to Haws is more of like, it's a signature of a sort of an interesting phenomenon. But in terms of like, trying to drive very, very large amplitude phonons, that would be sort of my reasoning of why that's interesting.
Steve, may I ask you to go back to Aaron Lindenberg's PhD thesis?
Okay.
About the boring even contribution. Because I think it's important for this school to reference this brilliant scattering description that you gave, right?
Yeah.
I think you said you have.
It's X-ray Brillouin scattering is all it is, yeah.
Precisely. Yeah. But I would like to point out that you explained it as if the X-ray would be reflective of surfaces, like it is true for optical light. But in fact, it's important that to see these oscillations in X-rays, you need a substrate that heterodynes the response of the crystal, right? You won't see the result of Aaron Lindenberg's thesis if you were looking at a thin film. And I think this is very important, that it's necessary to not reference to a reflection from a surface, but to a reflection from a bulk. But this doesn't.
You mean if you had a freestanding thin film?
Even if the substrate is simply reflecting at a different Bragg angle, you don't have an interference of the Bragg reflection of the substrate.
But you still have the outer surface.
Yeah, but the X-ray doesn't reflect from the surface, at least not so much that you would have a heterodyne effect. And that's why you actually never see these interference fringes in thin film or at grazing incidence. But I think the way that you illustrated this is good to see that it's brilliant scattering. It's the same as we see in optical.
Yeah, okay, I'm not 100% sure I agree with never see it in thin films.
We can think about it. I'm pretty sure that's correct. Okay, now let's take more questions.
So if you just have static elastic scattering in whatever direction this angle corresponds to, you would see something, right? If you have a thin film and you have
You will have a remainder of the crystal truncation line.
as long as there is some elastic field that is not trying to bend it.
I mean, that should be sufficient to heterodyne. It may not be a bad heterodyne.
And thin films usually, if it's thin enough, you'll have this ripples, finite size segments. And those will have contribution at certain
I mean, yeah, if you look at the...
Okay, but the heterodyne reference doesn't come from the crystal surface, but from the crystal. Anyway, let's discuss it later.
It's a diffraction.
No, but I mean, you also have... I mean, I'm sorry, if you have a bulk... Oh, sorry, maybe we should discuss it later. Okay, yeah, let's do the questions, yeah. Sorry.
Some people want to know the answer.
Oh, okay.
I don't know the answer.
But I mean, if you have a bulk, I mean, you have no substrate. You just that's all you have is a substrate. Then it is. You can think of it as it. I mean, these. If you do lineouts like this corresponds to a crystal that has this thickness.
But there's the unexcited crystal behind, which scatters the X-ray.
Right. You need two surfaces if you want to have interference, right? You have this. This is essentially your unexcited crystal, and this is your excited crystal, as far as the strain field goes. So you have one interface, and you have this interface, and they interfere with each other. No, but there's no other interface to scatter from. I mean, where else is you going to have an interface?
the X-ray scattering comes from the Bragg diffraction of the excited and the
Yeah,
non-excited
yeah, sure,
materials,
but
and it's actually the same thing. I think we're not disagreeing at all, except I think it's a little bit hard to think of the X-ray being reflected from a surface because it's reflected from
oh yeah, sure, but it has to be within the it has to be within the acceptance of the Bragg. Yeah, yeah, sure. Yeah, okay.
more questions.
Hmm. I mean, the reason why we did it in iron is because we could get samples that were of sufficiently high quality. The problem, one of the major problems in this experiment is you need samples with a really good transverse coherence, spatial coherence. Um, and actually, yeah, you have to go through a bunch of samples and screen them beforehand. Yeah, I mean, in terms of enhancing the effect, I mean, it's what we see is essentially equivalent to more or less what you would expect within a factor of 30% if all the angular momentum were transferred to the lattice in this form. So, I mean, we got like 80% or something of that. So it's within our error bars. It's basically saying that almost all of it's transferred. So you would need to have a system that demagnetizes on a similar time scale, or at least faster than these phonon periods, and has a larger transfer of angular momentum, which was not at least within the repertoire of what we were able to grow. So like I think you can have a larger magnetic moment, but then it's harder to do you have a smaller demagnetization step. So I think in terms of like swapping materials, I don't see a huge amount of hope of looking at a larger effect. What we're mostly interested in is designing samples that have a bit more structure to take advantage of, to look at multiple interfaces and have them constructively interfere. And so we could look at higher wave vectors with like a multi-layer of the sample, and then we can get higher sensitivity at higher Q vectors that way. If it were on for a long time, yeah. Well, in principle, if it were isolated, it would actually start rotating, yeah. Yeah, that's why I was trying to be careful not to call it a shear wave. I was trying to call it a displacement wave. No, no, clearly not. No, no. I mean, it's just seeing a shear wave. I mean, a shear wave by itself doesn't contain angular momentum. It's the point is though that this wave that we observe would be a direct consequence of this strain being applied, and the rotation is not. All we can do is we can look interferometrically at the relative positions of atoms. We cannot measure the entire system and say whether there's a rotation of the whole thing. It's basically just you hit it with an 800 nanometer laser. It's not even a fiber. It's a film on a substrate, and then you have a fairly large pump spot. Exactly. Yeah. Yeah.
and you keep longitudinal interface to the incidence angle immediately generate.
I mean, that would be a possible effect. I mean, you could argue that that would be the case, but that wouldn't depend on the initial direction of the magnetization. So that should be averaged out.
Okay, last question, I guess, for the.
Somebody
No, it's
It
okay.
was just you.
Prefer the. Okay, go ahead, Mark.
So I was in the magnetization breaks time reversal symmetry, right? So I assume that this circular dipole or this strange lattice phonon that you have there somehow has to have some sort of broken time reversal symmetry.
Yeah, that's the same. I think that's the same thing that we were talking
So
about
if you
there.
look at minus q, which you expect
Ah,
nothing, instead of
look at minus q.
mu minus q, uh, right? The breaking time reversal symmetry breaks q minus q symmetry. The problem is that
I'd have to think about that. I don't know.
the problem is that hard to look at minus q because that's inside.
Yeah, but even not thinking about that, I'm not sure. I'm not sure.